This is the first of two video lessons that are going to cover the topics of parametric equations, vectors, and polar equations. In essence, we can do one exercise that covers all three of those topics, but I neglected to write that this is just part one, so there will be a second video. Given the length of the exercise, you're probably going to want a break in the middle anyway. So hopefully you've read the situation here. What we have is an elliptical track, right, that a mouse is running around. He's doing it in a counterclockwise motion, and he's making it around the track once every 12 seconds, starting in the 3 o'clock position over here, the 0.50. Just to get started, we want to make sure we have equations in a couple forms for this ellipse. Hopefully you remember how to get an equation of ellipse from, say, your Algebra 2 class. The general form of it, you might recall, is just x minus h squared over a squared plus y minus k squared over b squared equals 1, where of course the h and the k are the center, or the x and y coordinates of the center of the ellipse. The a is the horizontal radius, since it's under the x, and the b is the vertical radius under the y. So in our specific situation, I think our center is at 0, 0, which is nice. So we just have x squared, and we also have y squared. We'll have the plus in the middle. And then our our horizontal radius is 5, so we would have a 25 under here, 5 squared, and then we're just going to have a 9 under the y squared, since our vertical radius is 3. So there's our equation in terms of just x and y. Notice there's no information about the fact that the mouse goes around once every 12 seconds. I'm going to go to a duplicate slide here since I'm out of room to write the parametric equations. So to write the equations, the parametric equations for this ellipse, let's do a little bit of review. Of course, we know parametric equations means we have both an x and a y equation in terms of t. And if we just write x equals cosine t and y equals sine t, then hopefully you recognize what shape this would give us. You know, when have we seen that the x is the cosine of an angle and the y is the sine of an angle? Right, that would just be the unit circle. Now, if we want to change the radius of the circle, right, then we multiply both the cosine and the sine by the radius. So the equations to really remember are x always equals r cosine t and y always equals r times the sine of t. I mean, that's just review from the fact that x over r will always equal the cosine of an angle, and your y over your radius will always equal the sine of an angle. Okay, so this would give us, let's see, these two equations here would give us a circle with a radius r, and the center would still be the origin. All right, now if we want an ellipse, of course we're going to have a separate radius for the x and a separate radius for the y. So it shouldn't be a surprise that all we need to do is have the x be 5 times the cosine of t, excuse me, and the y is going to be 3 times the sine of t. All right. And the other good news about this is we know that if we plug in 0 for t, time t equals 0, we're going to get back 5 for the x coordinate and 0 for the y coordinate. You know, if you just plug 0 in for t right here. So we know we'll be starting in the 3 o'clock position with these equations, and that's of course the easiest way to do it, just start in the 3 o'clock position. Alright, now just to say, if we wanted to change the center of the circle, we could either add or subtract numbers from the x and the y, and that would just shift our ellipse you know, either to the right and up or wherever we need to go. The thing we need to deal with now is, right now the way we have it set up is that the mouse, or if we were to trace this thing around, it would take to go one revolution or through one cycle, it's going to take 2 pi units of t to do that. Okay, or in other words, right now the period of our equations is 2 pi. We want the period, right? We want our period to be 12. Okay, that's what we're shooting for. Hopefully you remember from pre-calculus that the number that controls our period is the coefficient in front of our t. Now right now that coefficient is 1. Now we could dig a little deeper to explain what I'm about to say, but you should have learned last year in pre-calculus this little formula that the period always equals 2 pi divided by b. Alright, which of course also means that b is equal to 2 pi divided by the period. So we're trying to determine our b, and we know the period needs to be 12. So therefore our b is simply 2 pi over 12, or in other words, pi over 6. So we have one more rewrite to do here. I'm going to do this in red. But now we have that x is going to equal 5 times the cosine of pi over 6 times t. And y is equal to 3 times the sine of pi over 6 times t. And this should give us what we want. One way we could check it would be just to plug in some key numbers here. We know that at time t equals 6, we should be halfway around. So if we plug 6 in for t, we would have pi, the cosine of pi, is -1, which would give us -5 for our x. And then if I plug in 6 here, I'll have the sine of t, which is 0, so that would just give us the point -5, 0. Let's try at time t equals 3. We know that we should be right up at the 12 o'clock position, so if I plug 3 in here, I would have pi over 2, cosine of that is 0, and then the sine of pi over 2 would be 1, so we'd have 3, so that would give us the point 0.03. So it appears that, that these equations are giving us the points we want. And so let's see, I'll just kind of circle this right here. So the pi over 6, that goes with these two. And when we were working with these two equations here, we had a period of just 2 pi. Not a lot of room there, but I squeezed it in. So now if we step back and look at our equations, we can see that the parametric equations here incorporate pretty much everything, all the information that's up here, not only the position, but also the time. And that's the beauty of using parametric equations. And hopefully if you kind of saw, how we went through this, it's not that hard to write parametric equations for ellipses. Circles are pretty easy too. And if we had the time, we could do hyperbolas without much trouble as well. So now we're just going to plug these two equations into our calculator and see if we don't get the same graph of the ellipse. On your calculator, you should start a new document and open up a graphs page. And the way you can get this entry line right here so that you can enter the parametric is by hitting the menu button and then doing option 3, which is graph entry edit, and then option 3 again should give you parametric. And you should see menu with x1 of t equals and y1 of t equals. So we'll just enter our two equations there that we have. And then down here, this is kind of a nice feature of the TI Nspire, is you can enter your t values right in here. So I decided to just go with one time around the circle from 0 to 12 and decided to make this step be 0.1. And if you do that and hit enter, you should get the graph of the ellipse here. Now one of the cool parts about doing this on the calculator is you can actually reenact the mouse running around the ellipse. What you do is you simply hit menu again, go to option 5, which is trace, and then choose option 1, graph trace. And of course it'll give you a little cursor on your graph like this. And what you'll need to do is type in 0 to get it to start, to get it back to the 3 o'clock position there. So just hit 0 and then enter, and you're back to there. And now if you want to actually see the mouse running around your ellipse, you just hold down the right arrow key of your calculator, and you'll see this little cursor just go right around the ellipse. And if you keep it down, it'll keep going. I believe it'll start back over and go through the cycle again. As we work through the problems in this exercise, feel free to come back to your calculator and run the simulation again. See how the mouse is moving? When does he speed up? When does he slow down? Can you actually see that as you hold down that right arrow key? We're going to first take a look at the mouse's velocity. And we're just going to, I chose a random time of t equals 8 seconds. And I'm asking you two questions. One is, what's the mouse's velocity then in the horizontal direction? What is it in the vertical direction? And this is one of the beauties of doing things parametrically, is we have already broken down the position of the mouse in the horizontal direction as being, x equals, oops, I need my pen, as being x equals 5 times the cosine of pi over 6t. And we've also have the vertical direction as being 3 times the sine of pi over 6 times t. So I'm simply asking you for the velocity when I've given you the position. So go ahead and see if you can get the correct number. Alright, and when I do the problem, this is what I got. So of course, if we're given position and we want velocity, we have to take the derivative, right? We need dx dt in this case, right? Distance over time. And of course our dependent variable is time, so that helps. So in the interest of trying not to use a calculator too much, see if I can do this without it, I went ahead and used the chain rule on it. And we have the negative sign as the derivative of the outside function, right? Leave the inside function alone, times the derivative of the inside function. Gives us negative 5 pi over 6 sine of pi over 6t. Plug in the 8. And we do end up with 5 root 3 pi over 12, which I pretty much, well, I guess actually I was able to do that without a calculator, because pi over 6 times 8 is just going to be 4 pi over 3. And that is, so this is one of our unit circle values, which would give us this, but then in the interest of kind of knowing what that number is, I did pull out the calculator. Looks like I left one thing off the end though. What are the units on this? I think we said our position was in feet, so of course, and we're taking, we're at 8 seconds, or we're taking 12 seconds to go all around, so our velocity is going to be feet per second here. And then we do the same thing with the y, and get dy dt, plug in the 8, and we have negative 0.785 feet per second as well over here. Now let's just take a quick look at the graph. If you want to be on your calculator and see where is t equal to 8 seconds, let's see, I know that, let's see, it's 3 seconds at top, and then 6, and then we'll be at 9 here, so 8 seconds is going to be somewhere kind of on this bottom part here. And does it make sense, let's see, let me just kind of mark where 8 seconds is. Does it make sense that our horizontal velocity as we're going clockwise, I'm sorry, counterclockwise around the circle, does it make sense that our horizontal velocity is positive? And indeed it does. We've seen this before. And that our vertical velocity would be negative. And I think we can see that. We're kind of going down, but we're also going to the right. And notice, of course, the motion to the right is much greater than the motion down, so it makes sense that the magnitude of our horizontal velocity is greater than the magnitude of our vertical velocity. Okay, let's move to the next problem, number 4. Hopefully some wheels are turning in your head about things you've done in physics. What we just figured out, right, were the components of our velocity vector for this mouse at t equal to 8 seconds, right? And this is how the AP people like to write a vector when you have it written as components. You've got, you just put these, I'm really not even sure what these are called. They're not really brackets, but you put these symbols here, kind of like angle symbols, and then you write the horizontal first, of course, and the vertical second. And, we could even kind of graph that vector right here. Just put it at the origin. Remember, a vector doesn't really matter where it's located. We're just concerned about, what its components are. So we have that right there. But now we want to determine what is the magnitude and direction for this vector. So this should be a pretty easy problem for you if you've had physics before, which I believe all of you have. But even if you had not had physics, and all you had was pre-calculus, you could approach this problem from just thinking of it as a conversion problem, right? You're simply converting from a rectangular XY system now to a polar system, right? Because all we're trying to figure out now is what is the magnitude, which we could call r, and what's the direction, which we could call theta, right, in standard position. We're just trying to determine r and theta from x and y. And we've got a number of equations that help us do that. Okay, just to kind of quickly review, we've already written some of them down here. We know that x is equal to r times the cosine of theta. Right? We were writing that down when we were parameterizing our ellipse. We also know that y is equal to r times the sine of theta. Now those two equations may not help us very much here because we know x and y. We're trying to figure out what r and theta are. But there's two more equations that also help us, right? I'm going to sketch a quick diagram just to help with this. Writing this diagram out a little bigger helps to see the relationship, right? We're just talking about a right triangle here. Whoops, I didn't put my little right angle in there. And so we've got the three sides of the right triangle. Of course, we know that the main relationship there is that x, well, I'll write as r squared equals x squared plus y squared. And then all we need now is an equation that involves x and y and theta, because other than that we've got all the others in there. And of course we can just pick on our friend the tangent function, right? We know the tangent of theta is equal to y over x. If you have these four equations in your toolbox, then you can convert anything from polar to rectangular or rectangular back to polar. And right now you need to go from rectangular back to polar. So go for it with your x and y that you have up here. Check and see if this is what you got. Okay, so just set up my Pythagorean theorem here. And of course I started out with just calling that r squared, but if we want to think about this in terms of vectors, what we're really finding is the velocity vector, which this is the notation I think you've used in probably physics class for the magnitude of that velocity vector. Anyway, it just ends up being 2.399, and of course that would be feet per second with our velocity. That's our magnitude there, and it should always be a positive number, right? Now the angle theta, of course, is going to kind of tell us if we're heading in, more of a rightwards direction or more up or more down, that kind of thing. So we've just set up our tangent equation here, and with my calculator I get negative 0.3335 radians in standard position. That seems about right, right? That would be a fourth quadrant angle heading down that way. You might have decided to just use one of these equations over here once you knew what r was, which is fine, but I'll tell you what, tangent is so nice because it's very easy to find all the angles. If we know there's more than one angle that's got a tangent that's negative on the unit circle, it gave us the fourth quadrant angle, the calculator did, and we knew that was correct, but if we had been heading in the opposite direction, okay, up in, that's the other quadrant, the second quadrant where you can have negative tangents, now all we would have had to do would have been to add pi to this number, and we would have had the correct angle. So that's the beauty of using tangent. You just add pi. If you don't have the angle you need, if the calculator didn't give it to you, then just add pi to it and you will have the one that you're supposed to have. Alright, well now we've got our velocity vector, magnitude, direction, as well as the components. We have lots of information about what's going on at time t equals 8 seconds. Just want to take a quick minute here to point out that this speed, or the absolute value of our velocity, the magnitude of our velocity that we found, is not constant. Okay, you might think it is because of, we're just using a calculator to plot this motion, but check it out and you will see that it's not. Let's check it out when t equals 3 seconds and when t equals 6, because those are easy ones to do. When t is 3 seconds, right, we're only moving in the horizontal direction. There's no vertical movement, so we can just figure out what dx dt is, all right, when t equals 3, we just need to figure out what is dx dt, and that will give us our actual velocity. And when t equals 6, then we can just figure out what dy dt is, and because there's no horizontal motion at all when t is 6. All right, give that a shot, and you can see that the numbers will not be the same as the velocity we found in number 4. All right, here's what I got. As I was in the middle of my computations, I realized, of course, that I needed to take the absolute value of dx dt so that I would just have a speed, because, of course, this is going to give us the negative number, negative 5 pi over 6, since the sine of pi over 2 is 1. But the absolute value would give us a speed of 2.6179, and then here's the speed at t equals 6. One is basically pi over 2. All right, and hopefully, if you check this out on your calculator, like use that graph trace again and see, you'll notice that the mouse is probably, or the cursor is probably moving as fast as you go through this 12 o'clock position, but then it does slow down as you get to the 6 o'clock. I'm sorry, the 9 o'clock position, and then it speeds back up. So our velocity, or our speed, was pretty close to the 2.6179, because at 8 seconds we were almost getting there, but it's a little bit below that. These are actually the greatest and the smallest. This is the maximum speed, and this is the minimum speed that we will have on this elliptical track. I'd like to point out also that if our track had been a circle, we would have had a constant speed all the way around. All right, but the fact that it's an ellipse really actually guarantees that we're going to be slowing down on the short ends here, or the long ends, I guess, and speeding up on the top and the bottom. So now we're going to turn our attention to figuring out what is the length of the elliptical track that we're using here. Okay. Now we could just try to go back and use the formula we learned back in section 7.4 for length of an arc, but since we're in parametric, we might want to try to adapt that formula. And so this is the formula they give you in the book on page 722. Now perhaps it makes sense to you, but I want to go through a quick derivation of it so that you can see this formula actually comes from the very same formula we were using in section 7.4. Okay, you might recall that I took kind of a simplified approach and said, all you have to do is get your the differential arc length. Okay, and we know that ds squared was equal to dx squared plus dy squared. Okay, and then of course that meant that ds was equal to the square root of dx squared plus dy squared. All right. And what we did before, just to remind you, is if we needed to be in terms of x, when we integrated, we would just factor out the dx squared, and if we needed to be in y, we factor out the dy squared. It kind of depended on whether you were given a function as y equals, or given the function, or given an equation as x equals, or something like that. Okay. What would happen is you would end up with, if you factored out the dx, you would end up with ds equal to the square root of 1 plus, and you'd have dy over dx squared, and then you'd have a dx outside here. That would be if you factor the dx squared out. All right, and of course if you factor the dy squared out, it would be pretty much the same thing, but you'd have dx over dy squared plus 1 underneath that radical sign. Okay, but we don't want dy dx because we're in parametric. What we want is dy dt, or even dx dt, or even both in this case. All right, and here's how we're going to get it. All right, we want to end up with a dt underneath each of these differentials, the dx and the dy. So we are going to actually multiply. Let's see, we've got ds equals the square root of dx squared plus dy squared And we're just going to multiply both the top and the bottom of this expression by dt. Okay, so we're simply multiplying by a special form of 1, dt over dt. Perhaps you are already seeing how this might play out, and if so, feel free to finish the derivation. Otherwise, I'm going to write it out here in just a second. So here it is. All right, so if we, what we're going to do is we're going to leave the top dt outside, out in the back, and we're going to multiply, we're going to bring that 1 over dt inside the radical, and of course when we do that, it's actually it's actually the square root of 1 over dt squared, right? That would give us 1 over dt. So now we can distribute the 1 over dt squared over the parentheses here, and we do that, and then I'm just going to write it so that it's dx dt squared plus dy dt squared. Remember, we already figured out what dx dt was, and also what dy dt was for our problem. The rest is just a matter of integrating, and so it'll look like this. Alright, so when we integrate both sides of the equation, of course integrating the ds is just going to give us s, and then over on the right we're going to do our definite integral, because we'll have some interval over which our t values are ranging, okay? And yeah, notice this whole expression here is in terms of t, okay? dx dt and dy dt are in terms of t, so that's good because we're going to integrate with respect to t. Alright, so it's really just the Pythagorean theorem, again, with the square root there, and we're integrating from over our t values. So go ahead and use this formula with our numbers and our functions. I think at this point we really need to just succumb to using the calculator to get our answers. So don't feel guilty about that, but show your work how you set it up, and then plug it in the calculator and get your number. And once you have that, then you might want to go ahead and find the average speed of the mouse using that answer. Alright, see if yours looks like this. This is quite a bit to plug into the calculator. I just plugged in, we already had the dx dt, there it is, and there's the dy dt, and of course we square them, add them together, take the square root. The nice thing about the calculators is you can enter it in exactly like this and make sure it's right, even with the t's and the dt's. It can look just like that. Hopefully when you hit enter you got 25.52699. If you didn't, you can check that again. What did you put for units? Well, yes, of course, with arc length, and then we are in feet. So let me add that to my answer. All right, so what does that mean the average speed of the mouse is using this answer? And of course, if the total track was that many feet, we can just take that distance, 25.52699, and divide that by 12, right? So it took 12 seconds to go around the track once. And so our average speed is about 2.127, and that now, of course, is in feet per second. Now, if you think about what we just did in finding the average speed, we followed the same procedure that we learned back in Chapter 4 for average value of a function. Okay, if you think about it, this is how we got our speed, right? We took the horizontal velocity component, right? The vertical velocity component. We squared them, added them together, took the square root. That gave us our speed. So we were looking for average speed. All right, that meant we had to take the integral of our speed, okay, with respect to time in this case, dt, from 0 up to 12, and then we divided it by 12 minus 0. By integrating the speed up here, our units on top ended up in feet, and then when we divided by 12 minus 0, that was seconds, and that got us back into speed. Just as a reminder with our integrating, we had basically this function up here was speed, so we had feet per second, right, on the vertical axis and we had seconds on the horizontal. So when we took the integral, we multiplied these two quantities, and that gave us feet on top, and then of course dividing by the seconds got us back into speed. In that case, it was average speed. So, so you might not have realized it as you were going through this, but you were actually following that formula that we learned back in Chapter 4. Number 7 asks us to check our arc length from number 6a but this time, getting it a little differently. We're not going to use t. We're just going to use x and y to do it. We already have an equation that's in terms of x and y, and so of course to get our arc length, this was that arc length formula I was showing you on an earlier slide, where it would just be the square root of 1 plus, this is dy dx squared, okay, and if we integrate that with respect to x, we should be able to get our arc length. Now, of course, with the equation we have of x squared over 25 plus y squared over 9 equals 1, we're going to need to probably solve this for just to get y equals. All right, so that might be the first thing to do, and then you can start to think about what your derivative of that function would be, and then go ahead, feel free to use a calculator to get the integral because it gets fairly complicated. All right, so check and see if you got this. Well, you'll know you were right if you got the same number that we got before in number 6, and that is what I got. If you got half of that number, then it could be that you were forgetting that the function, when you take the square root, let's see, you subtract the x squared over 25 over, you can multiply over by 9, then you got to take the square root, but it's really the plus or minus, but we can only deal with one at a time, so we're just going to take the top half and go with the positive of that, okay? We get y prime. I cheated a little bit and plugged into my calculator and got that for y prime. So our arc length, since it's just the top half of our ellipse, we need to double it, right? If we go from -5 to 5, multiply it by 2, and then we've got the square root of 1 plus f prime of square root of y prime squared dx. And it seemed to work. It's really nice when you can corroborate something new that you do with something that you've done previously. Okay, we're going to tackle number 8 as the last part of this video. Keep in mind this is just part 1, and there is a part 2 that will deal with the second sheet of paper in the exploration that you have. You can imagine that since we've already dealt with the velocity side of things, then to get the acceleration, all we have to do is just kind of repeat what we just did in going from position to velocity. Now we're just going to do the same thing to go from velocity to acceleration. So here are our equations for the velocity in the horizontal direction and the velocity in the vertical direction. So keep in mind the units on these are in feet per second for both of these, okay? Which means if we were, to graph each one, we'd have feet per second on the vertical axis, and of course the variable t is in seconds. So if we want acceleration, then of course we need to, this is t here, we need to get the derivative of this. So in other words, we're going to need to be finding d dt of dx dt, right? Which is, as we know, the second derivative. As far as the notation goes, remember what that gives you is we say it would be d squared x over dt squared. Now the notation's not great. We really should probably have parentheses around the dt, okay? But that's how we notate it. So you just want to get your second derivative in terms of t, and you will then be in, that will lead to feet per second squared, right? Or feet per second. Put the square on there. All right. Now once you've gotten your components on your acceleration, then you still have a little more work to do, because what we mean when we say determine the acceleration vector here, we actually want the magnitude and direction, okay, of of our single vector that we have. We'll have the components, but then we need the magnitude and direction. Feel free to use your calculator to do the computations, though taking the derivatives of these two functions is still doable, very doable without a calculator. But at this point, we've kind of seen how that works, and if you want to use your calculator to help you do that, I'm fine with that. All right, so go for that, and you can check your work with what I have. All right, see if you got this. All right, so a lot of scribbling on this page now. On my calculator, I took the derivative of the dx dt equation and got this right here. And then I plugged 8 into it and got this for an exact answer, and I'm just going to go with the approximation of 0.685. And then we did the same thing with our dy dt equation and plugged in the 8 and got 0.7122. So this is our acceleration vector, its components. And if we need the magnitude, then we're just going to do Pythagorean theorem on those two components, and we get 0.9884 feet per second squared. And then I just use my tangent formula to get my direction. And just to kind of check and make sure that this angle is correct, we know 0.804 is in the first quadrant, right? Because pi over 2 is 1.57, so we're not quite up to there. So should we be in the first quadrant? And indeed we should be. If we look at our two components, the x is positive and the y is positive, so that happens in the first quadrant. So we know we have the correct angle. If both of our components had been negative, then we would have added pi to that answer to get the correct angle in the third quadrant. So when looking at our two vectors for velocity and acceleration, can we answer the question as to whether the particle is speeding up or slowing down? Well, we certainly can tell a couple of things from the components, right? If we look at the horizontal velocity and the horizontal acceleration, since they both have the same sign, right? This goes all the way back to what, chapter 2, or I think it was chapter 2. Since they both have the same sign, that's speeding up. But when we look at the vertical direction, they do not have the same sign, so we're slowing down in the vertical direction. All right, so which one kind of wins? It does appear that perhaps the horizontal is going to dictate more of the motion because that magnitude is certainly much greater. I'm not sure if we can really tell anything by looking at the magnitude and direction of both vectors. Certainly the direction might tell us a little bit that most of the motion, at least most of the acceleration, is maybe at a steeper angle than the velocity is. Steeper angle in the positive direction, whereas as opposed to the velocity's angle, in the kind of more of a negative direction, or towards the fourth quadrant. But I think knowing what we see in the components, that's probably an easier way to see whether we're speeding up or slowing down. And of course, when we look at the graph, I think that's maybe the easiest way to see it, that on our ellipse, we are definitely at a point where the particle is reaching its maximum speed as it heads back towards the 3 o'clock position. We know the maximum speeds are at the 12 o'clock and the 6 o'clock positions. All right, well that does it for part 1 of this exploration, and you might want to take a break before you take up part 2.